So in this video, I'm going to demonstrate to you a little bit about the need for a t-interval and how we would know how many standard errors to extend out and basically what value to choose for t depending on the sample size. So I'm going to start off by demonstrating to you a uniformly distributed population. So what I'm going to do is I'm going to take the super large number of observations from a uniform population here. I'm going to run this first part of the code, and you're going to notice that y is over here, y has 100,000 elements, and y represents some large population of uniformly distributed values between 0 and 50. Okay, so what I'm going to do now is take samples of size 15, and I'm going to find the mean of each sample of size 15. I'm going to plot it here on the right. And you can see, as we talked about with the central limit theorem before, sample means tend to distribute normally. They're distributing around the true population mean of 25. And these bars here signify extending out 1.96 standard errors in either direction from the population mean. So that means that 95% of the time I'm going to get a sample mean that is within 1.96 standard errors. Therefore, if I take my sample mean, so when I do inference, all I have is my sample mean. If I extend out 1.96 standard errors in either direction from my sample mean, then I would include the population mean 95% of the time. 5% of the time I'm going to be outside that range, and that interval won't quite reach the population mean. Okay, so to demonstrate this, I'm going to run this first simulation here. And what this simulation does is it's taking the true standard error for my sample mean, because if I know the population, I can calculate the standard error of my population. And so I'm going to run this simulation to see that with 100,000 samples and calculating the confidence interval, my confidence intervals for each one should include the population mean about 95% of the time. So in this simulation, it was about 94.96%. If I run that again, let's see what happens here. We get 95.005% of the time. So just demonstrating that about 95% of the possible sample means produce confidence intervals that include the true mean by using the actual standard error for my sample mean in that calculation. However, what we're doing with the t-interval is we're not using the population standard deviation in that calculation. Instead, all we have is our sample standard deviation. And I'm actually going to change this back to 1.96, which means that our standard error is only an estimate of the actual standard error for our sample mean. There's going to be a little bit of offness here. I just made that word up. A little bit of error here. Where sometimes my standard error estimate is going to be a little bit bigger than the real standard error, sometimes it's going to be a little bit smaller. And so with that, that's going to affect how often my confidence intervals correctly include the population mean. So if I run this using my estimated standard error, using only my samples of size 15 to generate that standard deviation estimate in the first place, I'm going to run this. And I'm not going to get 95% of my intervals containing the true mean this time. Instead, I'm going to get some value, in this case 92.9% included the true mean. And if I do this again, I'll get another value. I'll get another percentage that's going to be less than 95. And here I get 92.7%. So you see that my intervals are not capturing the true mean 95% of the time. That little bit of error using my estimated standard error, because I'm only using my sample standard deviations, is causing that problem. So I need to extend out a little bit more than 1.96. I'm going to try 2.145. And let's see how accurate my confidence intervals are now. So if I just stretch them out a little bit farther when I use an estimated standard error, this should improve, and there we go, 94.85. If I do this again, I should get, again, somewhere right around 95%. And again, maybe a little bit short, so maybe it's, if I was more precise, maybe it's 2.14, 5 or something like that. But I am kind of in that 95% neighborhood. And as we mentioned before, this does depend on our sample size. So if I was taking larger samples, like samples of size 30, um, this would not have as much error using my estimated standard error. So I'm just going to kind of run down here and show you. If I change this back to 1.96 and run this again, with these larger samples, I have more accurate sample standard deviations, giving me more accurate standard error estimates. And now you'll see that my confidence intervals are improving to about 94% accuracy. So I don't need as much error correction this time. I think somewhere in the neighborhood of 2.03. I didn't actually try this before, so I don't know if this is quite right. But I just know it should be a little bit higher. But we're going to run that again, and let's see how our accuracy goes this time. And always takes a little bit of time there. So a little bit better, so I guess a little bit more than 2.03. But you get the idea that this is that t-value that I'm plugging in. And the larger my sample size, the less I have to add, the less error correction I need. But when my sample is smaller, it's more noticeable, and I really do need that error correction to ensure that my confidence intervals really are containing the true mean, the appropriate percentage of the time that I'm requesting.